Today we want to continue talking about vectors, and I want to briefly go over operations on vectors. So we have these things called vectors. We need to know how our operations work with these vectors. So by operations, I mean like addition, subtraction, and multiplication. We have a new object. We need to see how it fits with our other math words. So here are the operations that we need to be familiar with on vectors. One of the operations that we always need when we have a new mathematical object is addition. Addition is like our base case. It is the base model operation. It's the operation on which everything else was built. There's addition. We only add things that are the same, and when we add them, it doesn't change what they are. That's how addition works. Then we know, for the most part, know how to add, for the most part, just in base 10, and with polynomials, base x. Everything else is variation on that. When you got common denominators for fractions, that's still in the category of we only add things that are the same, and when we add them, it doesn't change what they are. Sameness for fractions is a common denominator. A half and a third, I can't half plus 2/3. I can't take the 1 and the 2 from the numerators and add them because it's one of these things called a half and two of these things called a third. That would be adding that 1 and 2 would be saying I have 1 cup of coffee and 2 pens. You don't have 3 of anything. You can't add that 1 and that 2 to get a 3. But if we convert the 1/2 to 3/6, and we convert 2/3 to 4/6, I hate sixths. We can say we can add those things because then they would be the same. 3 of these things called over 6, and 4 of these things over 6. So we have 7 over 6s. So the same holds true with operations on vectors. If you want to add a couple of vectors, they have to be the same kind of vector. So I could, for example, take the vector 5, 3, 2, and add the vector -4, 0, 1. I haven't taught you how to add vectors yet. What's the sum of these vectors? I can sense your thoughts. You're thinking it, even though you're not saying it, which is okay. It's 8 o'clock class. No one wants to say anything. So let me read your mind. Someone is thinking 5 minus 4 is -1. I'm just going to add the corresponding components. 3 plus 0 is 3. And 2 and 1 is also 3. The great thing about vector addition is it works exactly like you think it works. You would just add the corresponding components. Five minus 4 is, like I said, +1. See, I did. I said +1. So +1 right there. I found my carefully planned mistake. 0 points for you, -10 for everybody else. I'm just kidding. It's -10 for everybody. Everybody's going to get the same grade in this class. We'll go Olympic style. We'll drop the highest score and the lowest score, then take the average of the rest. I'm just kidding. That would be ridiculous. We're just going to take the lowest score. This is forced helping. I'm just kidding. That's a situation right for extortion. So vector addition, the great thing here is it works just how we think it would work. I haven't had enough coffee yet, so I have to fake enthusiasm by putting exclamation points at the end of everything. Here I have a vector from R3 and another vector, but it's from R2. We cannot add these vectors. They don't have corresponding components. They are not the same things. You're trying to say $5 plus 7 pencils. How much is that? That's not 12 of anything. We can't add those things. They're not the same. Cannot add these two. They are not the same. Pretty much how you guess it would work, or in this case, not work. Any questions? We also want to be able to visualize vector addition. So if I add two vectors, if this is the vector v, and I want to add this to a vector w, what we do is we just put them end to end. First we do v, and then we'll draw the vector w. The sum of those vectors will start at the end of our first one and go to the end of our second one. So this would be our sum vector. We are calling this addition. We have assigned the phrase, the term addition to this, and addition should be commutative. Multiplication doesn't need to be commutative, but addition should be commutative. So what if I wrote w first and then attached v to the end of it? We'll just have the other half of the parallelogram. So if I put w first, and then attached v, to the end of w, we end up at the same place. It's good that it makes sense in this visual case because it's the only thing that we could conclude in the adding components case. 5 plus -4 is +1, even if you put the -4 first. -4 plus 5, still +1. Vector addition is commutative. Stuff that you call addition needs to be commutative. Any questions? Is everybody okay? Like I said, Calc 3 is the easiest one. That's why everything is so simple. Some of you are optimistic. You're like, oh, yes, Calc 3 is simple. We believe you. And then some of you are suspicious. You're like, oh, no, it's not going to be like this forever. I've seen notation in vector calculus, and I cannot read it. We know shit going to get weird. No. It stays simple the whole time. Oh, sorry. I have a cough. That wasn't an evil laugh. I mean, sorry. Maybe I should be wearing a mask. A mask of evil. No, so here's one of our operations. It's vector addition. It works exactly how you think it would work. The other operation that we have that works exactly how you think it would work, we just need to visualize it, is scalar multiplication. Number 2. Similarly, I'm not going to write this out in general. I'm just going to give you an example and say extrapolate. Scalar multiplication means we're going to take a vector and multiply it by a scalar. So I'll take -4 times 5, 3, 2. So what I've got is I've got a scalar, -4, times a vector. What we're talking about here is scalar times vector. In vector addition, we had a vector plus a vector. Unsurprisingly, when you multiply a vector by a scalar, you just multiply every component by that scalar. So we end up with -20, -12, -8. Multiply each component by the vector. Sorry, multiply each component by the scalar. Which is pretty much how you guess it would work. This is what we assumed worked, how it worked. This is how we assumed it worked yesterday when we looked at the vector 5, 3 as 5i plus 3j. Visually, multiplying a scalar by a vector changes the magnitude, but keeps the direction. Unless we multiply by -1, in which case we just reverse the direction. So if we've got a vector, and I multiply this vector by 2, I just take this vector and it becomes twice as long. So the vector v up next to the vector 2v Maintain the direction. I just adjust the magnitude. If we multiply by -1, we think of that as changing the direction, but it's still on the same line. So it reverses the direction. We need to know what we do with the components. We need to be able to visualize what's going on with the vectors when we add them. How's everybody okay? Everything so far has been exactly like you would guess. You could put this on a quiz and hand it to a student and not explain anything about vectors. And the students be like, oh, how are we supposed to do this? And I could be like, oh, yes. And be like, oh, all right. This is what you would probably come up with. Like in linear algebra, when you add matrices, they have to be the same size. If I gave you two different size matrices, actually, in that case, if I give you two different size matrices, you'll make up some weird stuff to do. Like just ignore the third component. You'll be like, well, I'll add the x's and the y's, but then I'll just keep the z because you said to add them. So I'll do something. Any questions, comments, deep thoughts? How's everybody okay? So we got vector addition, scalar multiplication. Those are our baseline operations. These are how we make linear combinations. Vector addition and scalar multiplication. If we use those to put vectors together, we're making a linear combination. That's what we're talking about, linear combination up here. We're just going to be using vector addition and scalar multiplication to combine the vectors. That makes a linear combination. The next category is going to be vector multiplication. How do we take a vector and multiply it by another vector? There are two kinds of vector multiplication. In vector multiplication, it's a vector times a vector. And we have two different multiplication operations. That's why I wrote out the word times rather than a symbol, because that's how we're going to differentiate the two. Also, the product will differentiate the two. So we're going to have two kinds of vector multiplication. One is called the dot product. And so we'll use a dot to indicate that multiplication. The other is called the cross product. This is one that we're going to use on R3. And we'll use an X for that one. The dot product is a scalar product. And it works for anyone. We're going to use this one all over the place. We're going to be calculating cross products only in R3. Calculus is this weird combination of math class and engineering class. We got to make some practical cuts. So cross product, we're going to worry about in R3. The dot product is a scalar product. That means the vector dot vector will give us a scalar. Vector dot vector is scalar. The cross product is a vector product. Vector cross vector will give us a vector. Two kinds of multiplication. Just like before, we have to know how to make this operation go, and we have to understand what it represents, what we can use it to represent. Is everybody okay? Simple enough? Everybody all right? Calc 3 is the easy one. It's hard to tell because everybody looks like this. Because it's like at 8 o'clock in the morning math class. No matter what I do. When class is easy, you look at me like this. When class is completely incomprehensible, you'll look at me like this. If I stood up here and set myself on fire, y'all would look at me like this. And then someone would be like, oh, is this on the final? Do we have to burn ourselves? Or do we have to burn the teacher? And then you're asking, like, your friend will be like, well, I don't know, but I hope it's the latter. So two kinds of vector multiplication. Vector dot vector, vector cross vector. So like I said, we need to learn how to dot product and why to dot product. We always lead with dot product because it is much easier. And we're just going to go with an example. I'll take the two vectors that I added before, and I will dot product them. Now the answer is going to be a scalar because we have vector dot vector equals scalar. So the way we calculate it is we find the sum of the products of the corresponding components. It's the sum of the products of the corresponding components. That is the dot product. Notice that this will produce a scalar. We multiply the corresponding components and add the results. Because of the process that we're using, this means that the vectors are going to have to be the same size. We can't dot product things that are different sizes. So, for example, I wouldn't be able to say 5, 3, 2 dot whatever I said before. I can literally just make up any two other numbers, but I want to use the ones from before, 7 and -8. We don't get to dot product these two vectors because there is no component, no z component of the second vector. There's no dot product. The vectors need to be the same size. Why do they need to be the same size? It was going to need to be the same size because I was going to start for some reason writing that word in cursive. And then there's like the extra. Does anybody learn? Do you learn cursive in school anymore when you're writing? I know some schools do, some schools don't. Here's the dick thing that older people do to younger people. They stop teaching the students a thing, stop teaching young people a thing, and then proceed to make fun of them for not knowing it. It's like, what the fuck, dude? You don't get to make fun of me for not knowing how to use a manual transmission if you never taught me how to use a manual transmission? You don't get to make fun of a generation that can't write cursive if you didn't teach them to write cursive. You know what I mean? Don't do that to your children. If you want them to write cursive, teach them to write cursive. Don't be making fun of people that don't know how to change their oil if you never taught them how to change their oil. You know what I mean? Changing oil is going to be a thing that goes away because we're getting rid of those kinds of engines. So, and the best thing to do is turn around and say the same people that are complaining about cursive and manual transmissions are also the same people that used to joke they don't know how to program their damn VCR. My VCR is still blinking 12 o'clock because I can't read the manual to figure out how to do it. You know what I mean? Don't take any crap from old people about the things that you do or do not know. Old people are just as stupid about stuff. You know what I mean? You know those emails you get from that Nigerian prince who's going to give you a lot of money if you just give him your banking information? You know why that existed? Because old people, these stupid kids, they don't know how to drive a manual transmission or change their oil or write in cursive. Oh, look, a Nigerian prince wants to give me lots of money. I'm going to send him my banking information. Don't take any crap from old people, because they're worried that you can't do things that are going away, but they can't do things that are coming straight at them. So just pat them on the head. It's like, oh, that's cute, Grandma. All right, what am I talking about? Oh, yeah. Old people are dumb. I'm sorry, old people. You're not dumb. You're just really ignorant. But then you're obstinate about your ignorance, and that makes you kind of dumb. Dot product. This is how it works. It's nice and straightforward. That's why I felt comfortable cramming it into the last 5 minutes of class. I haven't talked about why dot product. This is how to dot product. What is this scalar going to be telling us? That's an important question that we need to address. But that sounds like a question for tomorrow. Any questions? All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. What's that? What's the point? It's so whenever you're writing, like the way I'm writing here, every letter is separate. So I write V, and then I have to up, E, up, cursive. It connects all the letters together. So rather than like having to stop between each letter, you can just kind of like keep flowing along. No, it was to kind of make your writing, as far as I can tell, it was kind of make your writing faster. But then you had to also learn to read it because the letters, because you're just like smearing everything together, the letters kind of look different. Well, I learned cursive when I was a kid. That's how, that's an old thing. Yeah. So, but for the most part, our communications, especially our professional communications, they're going to be typed. So if a school is teaching students cursive, but not teaching them touch typing, then they're doing it wrong. Yeah. So
I never saw the point of that. Like, why would I?
when, and also at first, so I think part of it was, it looks very, if you haven't learned it, it looks like a mess because everybody's writing is different, and it's much harder to read than just printing things. But it's also much faster than just printing things if we're all good at it. But what's even faster than that is typing. And so that's why it's a reasonable thing to make it go away. And only old people will complain that people aren't learning cursive anymore. And it's fine if it goes away. It'd be nice if some people remembered it, because we'll find a lot of old documents like back in the day, or when you wrote correspondence and put up letters like on paper. that's going to be written in cursive. So it would be nice if someone could read those hieroglyphics. But we don't need everybody to be able to do it, because what we really want, if we really want that information, aside from the artifact of like a paper from a piece of paper from the Civil War, that's interesting as an artifact. But what's also interesting is what's written on the page. If we can't read that, then there's no point. But it's not like everybody needs to read that, right? It's not like everybody needs to be able to read and understand ancient hieroglyphics. But it's really important that some people do, so they can share that knowledge with the rest of us. Oh, I'm still recording. Never mind, that wasn't math stuff. It's not on the final. No cursive or hieroglyphics on the final.